Imagine, you throw away an old washing machine, not even suspecting that it could live another life. But where does your appliance actually end up after it's been taken away at a discount or for free? Is it really recycled or just buried under a layer of earth? Behind every seemingly dead machine stands a whole industry of destruction, separation, and material revival. Giant shredders, magnetic separators, eddy current fields that separate aluminum from steel with centimeter precision. And at the end of the video, you'll learn something that's not mentioned in any trade-in advertisement. What really happens to your old appliance after it disappears from your home? Many major brands and electronic stores offer a trade-in program or free removal of old appliances when you buy a new one. For example, in the United States, companies like Whirlpool, LG, and Samsung have such programs, and in Europe, initiatives like the Waste Electrical and Electronic Equipment Directive are in place. The terms can vary. Some companies simply take the appliance, while others offer a discount on a new purchase. Whirlpool in the United States might offer a $50 to $100 discount on a new appliance for an old washing machine. LG and Samsung sometimes offer $100 or $200 as part of promotional programs. In Europe, some programs allow you to get up to 10% off a new appliance. But more often than not, the discounts aren't very large. Most companies view this as an environmental initiative rather than a way to attract customers. In many cities, there are electronic waste collection centers where citizens can bring old washing machines themselves. Often these centers work in cooperation with municipalities or private companies. In some countries, including Germany, the United Kingdom, and the United States, there are municipal services that provide collection services for large electrical appliances. For example, in New York City, you can order a free pickup through the NYC Safe Disposal program. Some companies are involved in secondary metal recycling, so they may buy the washing machine or take it for free. They send the appliance for dismantling, where they extract metal, electronics, and plastic. First, the machines are sorted into categories: working, partially working, and non-working. Working ones can be repaired and resold, while those beyond repair go to dismantling. Dismantling begins with removing the outer panels, doors, and drum. The motors, electronics, wires, and pumps are separated, as they can be reused or melted down. Metals are sorted separately: stainless steel, aluminum, and copper. Plastic parts are also sent for secondary recycling. This process can be done both manually and with the help of special automated lines that shred the casing and separate the materials using magnets and air separators. Automated lines for recycling washing machines consist of several stages, each responsible for separating different materials. First, the machines are fed onto a conveyor belt, where they are shredded by powerful rotary shredders. The blades of these shredders are capable of tearing metal and plastic casings into fragments ranging from 3 to 10 centimeters in size. After shredding, the materials pass through magnetic separators. They attract ferromagnetic metals, such as steel and cast iron, separating them from the rest of the components. Next, an eddy current separator comes into play, which uses a magnetic field to push out non-ferrous metals, including aluminum and copper. Plastic and light materials are separated using air separators. Powerful streams of air lift the light particles up, sending them into special containers, while the heavier ones remain on the conveyor. At the end of the sorting line, the remaining materials are additionally checked with optical scanners that analyze their composition and direct them to the appropriate sections for further processing or disposal. After the materials have been sorted using air separators and optical scanners, they go to separate processing lines. Plastic, metal, glass, and other materials are processed for further use or recycling. The remaining metals, such as steel parts, are sent to metallurgical enterprises for remelting and further use in the production of new goods. Magnetic separators effectively extract iron and steel, which are sent for remelting. Plastic parts are shredded and pressed into briquettes. These briquettes can be sent to specialized enterprises for the production of new plastic products, or for use as secondary raw materials for new technical devices. If the washing machine has glass elements, for example, doors or windows, they are thoroughly cleaned of any contaminants and can be melted down to produce new glass. The remaining materials that are not recyclable, for example, certain types of rubber or mixtures of materials, are sent for disposal or burial at specialized landfills. Such sorting and recycling lines significantly reduce the amount of waste that ends up in landfills and help return raw materials to the economic cycle. In some cases, for particularly complex materials, additional technologies are used, such as thermal decomposition or chemical treatment. They are used for materials that cannot be simply separated by mechanical methods, or that require additional processing to prevent contamination or harmful emissions. For example, some plastic components that contain a combination of materials such as plastic with metal inserts or rubber parts. Such materials may not be subject to simple sorting and require special processing to separate the components. Often, rubber elements, especially with the addition of chemical compounds, are not effectively recyclable due to their complex structure. For such materials, thermal decomposition or other chemical processes may be used to break them down into simpler components that can be reused or disposed of. In some cases, when an appliance contains toxic substances, for example, mercury in old relays, batteries, or lighting devices, such materials must be processed by special methods. This can be a chemical process that neutralizes harmful components or isolates them for further safe disposal. Polyurethane or polyester materials, which are often found in wire insulation or in various components of household appliances, can be subjected to thermal decomposition to separate them into simpler components that can be recycled. In cases where washing machines or other appliances contain complex composite materials that have several layers of different substances, for example, plastic with metal or fibrous components, special processing may be required to separate these layers and for the subsequent recycling of each of them. In general, such technologies are used to ensure maximum efficiency of disposal and to reduce the negative impact on the environment, as improperly processed materials can lead to pollution or the leakage of dangerous substances. Imagine, glass that once shattered into deadly sharp fragments now saves lives. How did humanity transform a fragile substance into armor for a car? And what is hidden behind this seemingly simple transparency? Every year, over 100 million square meters of automotive glass are produced worldwide, enough to cover the area of an entire country. But the real magic happens where molten stone is transformed into a perfectly smooth surface, in furnaces that reach temperatures of over 2,700 degrees Fahrenheit. How did ordinary quartz sand become the foundation of safety technology, without which we cannot imagine modern transport? Watch until the end, and you will learn what accidental experiment changed the history of automobiles forever. The history of automotive glass production is closely linked to the development of the automotive industry, which emerged at the end of the 19th century. The glass used in cars today has come a long way in improvements, making it safer, stronger, and more functional. When the first cars began to appear, they were initially not equipped with glass at all. The open body design only partially protected passengers, and dust, wind, insects, and other hazards made trips very uncomfortable. Later, as cars became faster, the need to install protection for the driver and passengers arose. The windshield began to be made from ordinary window glass, which, although it provided some protection, had a serious drawback. During accidents, it shattered into large, sharp fragments, leading to numerous injuries. The first revolutionary discovery in the field of automotive glass was the creation of laminated glass. This happened by chance. In 1903, the French chemist Edouard Benedictus accidentally dropped a flask with a nitrocellulose coating. The glass cracked but remained whole thanks to a thin layer of plastic. This accident inspired the scientist to create multi-layered glass, which later became the basis for triplex. Already in the 1910s, laminated glass began to be used in premium class cars. Its construction consisted of 2 layers of glass, between which a thin, transparent film was placed. In the event of an impact, the glass did not shatter, and the cracks remained on the film. In the 1920s, laminated glass began to be actively used in the production of windshields. Its main advantage was increased safety. Even during serious accidents, the fragments did not fly apart but remained in the polymer layer. The next stage in the development of automotive glass came in the 1930s, when the technology for producing tempered glass was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it broke, it disintegrated into small pieces with blunt edges, which minimized injuries. In the mid-20th century, tempered glass began to be used for the side and rear windows of cars. It was cheaper to produce compared to triplex and provided a sufficient level of safety for these parts of the car. In the 1950s and 60s, automotive glass became even more perfect thanks to the development of technology. During this time, various important changes took place. Improvement of triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production. The automation of production processes allowed for a reduction in the cost of automotive glass, which made it more accessible to the mass market. Sun protection coatings. For the first time, special coatings began to be used that blocked ultraviolet light and reduced the heating of the car's interior. One of the most important technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, allowed for the production of perfectly smooth glass by spreading the liquid glass mass over the surface of molten tin. Thanks to this method, glass became more uniform, strong, and accessible for mass production. The float method is still the basis of automotive glass production today, ensuring its precise dimensions, surface smoothness, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 1960s, heating filaments began to be installed in the rear windows of cars, which prevented fogging and freezing of the glass. In the 1980s, glass with special metal coatings appeared, which reflected sunlight and reduced the heating of the interior. Glass with ultraviolet protection. Thanks to the introduction of new technologies, automotive glass began to provide almost complete protection against harmful radiation. And then we begin the modern period of automotive glass production, which we will talk about now. And we will start with glass for cars. Automotive glass is divided into several types depending on its purpose and production technology. Windshield. Usually this is multi-layered glass, which consists of 2 layers of glass, between which a polymer film is located. Such a design ensures that upon damage, the glass does not fly into sharp fragments. Side and rear glass. Most often this is tempered glass, which upon impact breaks into small blunt-angled pieces, which reduces the risk of injury. Panoramic roofs or other special types of glass. Laminated or tempered glass with a special coating for protection against ultraviolet radiation is often used. The main components of glass are natural materials that are mixed in certain proportions to obtain the desired properties. Quartz sand is the main component of glass, which ensures its transparency. It must be extremely clean and contain a minimum of impurities. Soda is added to lower the melting temperature of the glass. Lime improves the mechanical stability and chemical properties of the glass. Additional additives used to correct color, transparency, resistance to ultraviolet light, and other properties. The raw material is cleaned, dried, and crushed to a uniform state. It is important that impurities that can affect the quality of the glass are maximally eliminated. After preparing the raw material, it is loaded into special furnaces for melting. This stage includes several important moments. Let's look at them together. Melting temperature. A temperature of about 2,732 degrees Fahrenheit is used to form the glass mass. In the melting process, the raw material turns into a uniform viscous liquid. Homogenization. The glass mass is mixed for an even distribution of components. This is important to avoid air bubbles or inhomogeneities in the finished product. Furnaces for melting glass are equipped with modern temperature control systems and process automation, which ensures high quality of the final product. After melting, the glass mass undergoes a forming process, which in modern production is most often performed using the float method technology. Feeding the glass mass. The liquid glass flows out of the furnace and onto a bath of molten tin. Thanks to the high density of tin, the glass mass spreads evenly over its surface. Under the influence of its own weight, the glass forms a perfectly even and smooth surface. By gradually lowering the temperature, the glass acquires hardness. At the exit of the bath, it can already be processed. The float method allows for the production of glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions required for automotive production. Automated cutting machines ensure the accuracy of the work. To prevent the formation of cracks and chips, the edges of the glass are ground. Each sheet is checked for defects, such as microcracks, bubbles, or other damage. Next, to ensure the strength and safety of automotive glass, it is subjected to a tempering process. The glass is heated to a temperature of about 1,112 degrees Fahrenheit. Then, the surface of the glass is rapidly cooled by streams of air, while the inner layers cool more slowly. As a result, stress is created, which increases impact resistance. Tempered glass, when destroyed, breaks into small, safe fragments, which minimizes the risk of injury. Next, for the windshield, triplex is used, a construction of glass and polymer film. Its production includes several stages. Joining the layers. A polymer film is placed between two glass sheets. The construction is placed in a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to a temperature of 284 Fahrenheit under high pressure. This ensures a strong connection of the layers. Triplex has high impact resistance, and upon damage, it remains in the polymer film, which ensures the safety of the driver and passengers. Next, to improve the properties of automotive glass, various coatings are applied to it. Anti-reflective coatings reduce glare from the sun or headlights of other cars. Ultraviolet protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings ensure that water runs off the surface of the glass. Heating elements. Thin heating filaments can be embedded in the windshield, which facilitate the removal of ice or fogging. To achieve the desired shape, special thermoforming installations are used. The glass is heated to a temperature at which it becomes plastic and is formed according to the given parameters. And so, we have reached the final stage. During it, each product undergoes a thorough check. Transparency and the presence of defects are checked. Next, the glass is tested for impact resistance and endurance to loads. Compliance with standards. The accuracy of dimensions, shape, and other parameters are checked. Then the finished automotive glass is packaged in such a way as to avoid damage during transportation. It is delivered to car factories or service centers, where it is installed in vehicles. The production of automotive glass is a high-tech process that combines physics, chemistry, and engineering. Thanks to modern technologies and strict quality control standards, automotive glass ensures safety, comfort, and durability. And just imagine how many stages the automotive glass had to go through for us to be able to monitor safety on the road and have the opportunity to admire the wonderful landscapes. It seems incredible to me. And you? Every year, over 900,000 aircraft engines are manufactured worldwide, hearts that push giants of the sky on journeys across continents. But have you ever wondered how this metal monster is born? One that operates in conditions of over 2,000 degrees and at speeds that could destroy any metal. Inside it, titanium bones, a nickel heart, and composite lungs. And then, technologies resembling alchemy, single crystals, vacuum casting, and 3D metal printing. But the main secret is not in how it's created, but what's hidden inside. Watch until the end, and you'll learn something that even Boeing engineers keep quiet about. The turbofan engines that push giants of the sky, like Boeing and Airbus planes, resemble something out of science fiction. However, they are a true embodiment of engineering genius. How are these amazing machines assembled from tens of thousands of parts and ingredients, like a puzzle? Ordinary metals are not suitable for their manufacture. After all, the engine must operate in conditions where the temperature can exceed 1,800 degrees Fahrenheit. This is a real inferno, and ordinary steel simply wouldn't withstand it. This is where titanium alloys come on stage. Lightweight, strong, and able to not melt in extreme heat. And for the hottest zones of the engine, nickel-based superalloys are used. By the way, this isn't just metal, it's 21st century alchemy. Composites, particularly carbon fibers, are used for the fan to reduce weight while maintaining strength. Such a high temperature arises from the process of burning fuel in the combustion chamber, one of the most important elements of a turbofan engine. During engine operation, aviation fuel, usually jet fuel, is mixed with air and ignites, forming hot gases. These gases are literally accelerated to insane speeds and temperatures, over 1,800 degrees Fahrenheit, and sometimes even up to 2,700 in modern engines. This level of heat is needed to get the most efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that spins the turbine and provides the aircraft's motion. And here lies the main challenge. The engine must not only withstand these extreme conditions, but also operate stably, without the slightest failure. That's why it uses super technological materials, like titanium alloys and special composites, which can withstand both high temperature and insane mechanical stress. You know what's incredible about the process of creating an engine? That even individual parts, like the turbine blades, are created with micron precision. For example, the blades are cast in a vacuum so that there isn't even the smallest crack inside. Some of them are formed to have a single crystal structure. That's when a piece of metal has no seams at all. But that's not all. 3D printing? Yes, that's used too. For example, for complex parts that are impossible to make with traditional casting. The turbine blades are the heart of the engine. They operate in the hottest zone and convert the energy of the hot gases into rotational motion. First, a model of the blade is created from wax. Yes, it looks almost like artistic sculpting, only here, precision down to the micron is important. This wax sample is then dipped into a special ceramic solution, which gradually dries, forming a strong mold. This mold is like a perfect cast of the future blade. The wax inside is melted and removed, and the ceramic is ready for the most important stage. Next, the show begins. In a special furnace, superalloys are melted, which include nickel, chromium, and other metals capable of withstanding temperatures above 2,000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But the secret is not only in the material, but also in the way it's done. To make the blade withstand gigantic temperatures and loads, it is often cast as a single crystal. This means that the entire piece of metal has no seams, micro cracks, or different grains, as in ordinary metal. Why is this important? Seams or micro cracks in such conditions are like a minefield. One mistake, and the blade shatters. Single crystals are grown through very slow cooling. The mold with the molten metal is gradually lowered into the cooling zone of the furnace. This process can take several days, but the result is a perfectly strong and durable blade. When the metal cools, the ceramic mold is broken, and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface so that it can withstand extreme temperatures even longer. And so, each blade is checked separately. If there is even the slightest defect, it doesn't go any further. Fuel injection nozzles, combustion chamber parts, or even compressor blades in aviation are made using 3D printing. For example, the company GE Aviation prints nozzles for its engines that weigh 25% less, but are 5 times stronger than traditional ones. Layer by layer, from powder and light, parts are created that allow planes to fly faster, farther, and more economically. First, engineers create a digital 3D model of the part with maximum precision. Here, every curved surface or cavity matters. Why? Because these parts often work in places where a millimeter can change everything, from the engine's efficiency to its reliability. The digital model becomes a map for the 3D printer, which knows where and how to create the required shape. Instead of the usual piece of metal, an ultrafine powder is used here. For example, of titanium, nickel, or Inconel, this is a super aluminum alloy. It looks like sand, but with particles so fine that they are almost invisible to the naked eye. The powder is poured into a special reservoir, and it becomes the building material. The principle of the printer's operation is simple but ingenious. It melts the powder using a laser or an electron beam. The laser heats the powder to such a temperature that it literally fuses into a homogeneous metal structure. Then the next layer of powder is applied, and the process is repeated. This method is called selective laser sintering or melting. And what's cool is that 3D printing allows for the creation of even the most complex geometric shapes. For example, parts with internal cooling channels, which are generally impossible to produce by casting or milling. You know, in traditional manufacturing, you often have to first make a large part and then cut off all the excess. This is not only time-consuming, but also expensive because a lot of material is wasted. But 3D printing works differently. Only what is needed is created without waste. The resulting part is not yet completely ready. After printing, it undergoes heat treatment. It is heated and gradually cooled to relieve internal stresses in the metal. Then comes the final grinding, polishing, or mechanical processing if precision needs to be adjusted. And of course, each part undergoes thorough testing. After all, everything here is serious. If a part does not withstand the load, the consequences can be catastrophic. The engine assembly takes place in a huge hangar, where every foot of space is occupied by tools, engine parts, and people in overalls who are intently working on something extraordinary. This place is the final stage of creating an aircraft engine. Here, individual parts such as blades, compressors, combustion chambers, and casings are transformed into a single whole, ready to lift an airplane into the sky. It all starts with the engine casing, which resembles a giant metal cylinder. This is the skeleton to which all other parts will be attached. The casing is made of titanium or nickel alloys, as it will have to withstand insane loads. Engineers work like watchmakers. The casing is secured in a huge machine tool to ensure everything is perfectly level. Next come the compressors, several rows of blades that are responsible for compressing the air before it is fed into the combustion chamber. The blades are installed one by one, as if decorating a giant wheel. Each one is checked by hand, as the slightest defect can ruin the entire job. After the compressors, it's the turbine's turn. These are the blades that convert the energy of hot gases into motion. The turbines are placed so precisely that the distance between the blades and the casing walls is sometimes measured in microns. Next, the combustion chamber is installed, the real hell of the engine. Here, compressed air is mixed with fuel and burned. Engineers install special nozzles that ensure a uniform fuel supply. And here, everything must be perfect. An incorrect nozzle angle, and the engine can lose efficiency or even fail. A central shaft runs through the entire engine, a kind of backbone. At one end of the shaft, a fan in the form of a huge wheel is attached to the front of the engine. At the other end, the turbine. When the turbine rotates under the influence of hot gases, the shaft transmits this energy to the fan, which sucks in air. Special robots are used to install the shaft. This part of the process requires surgical precision, as even a microscopic misalignment can cause vibrations that will kill the engine. When the internal part of the engine is assembled, the external systems are added. Fuel pipes that supply fuel to the combustion chamber, an oil system that provides lubrication for all moving parts, and electronics because the engine is literally packed with sensors that monitor temperature, pressure, speed, and much more. These elements are attached using cables, tubes, and bolts that must withstand not only vibration, but also extreme temperatures. After the assembly is complete, the engine is not sent to the aircraft right away. First, it is attached to a test stand, where real flight conditions are simulated, from takeoff to turbulence at an altitude of almost 33,000 feet. This is the most spectacular stage. Starting the engine at full power is accompanied by a roar that can be heard for several miles and bright gas streams. The engine runs under load for hours, and engineers check it for strength, endurance, and efficiency. When the engine passes all tests, it is disassembled, the main components are checked again, and then it is finally assembled. The finished engine is packaged and transported to a Boeing or Airbus factory, where it becomes part of a new aircraft. And so, part by part, engineers create the heart of an airplane, which is capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Let me know if you would like to see more videos like this. Every year, over 500 species of bamboo are grown worldwide, and China holds the richest treasure of them all. Imagine this: 16 million acres of lush green forests, an area larger than all of West Virginia, pulsing with life and growing so fast you can literally watch it with your own eyes. Some species can shoot up more than a meter in a single day. This is where a $27 billion industry begins, an industry that feeds, clothes, and even builds entire cities. But behind this green marvel are secrets you've likely never seen. Watch closely. If you stay with this video until the end, you'll discover something that will make you see this simple grass in a completely new light. China is the undisputed king of the bamboo world. The country is home to over 500 bamboo species, and its bamboo forests cover more than 16 million acres. That's more land than all of West Virginia, covered entirely in a sea of green. This massive natural resource is the foundation of a multi-billion-dollar industry. China produces 80% of all bamboo products in the world, exporting them to more than 100 countries. It all starts not in a noisy factory, but in the silence and greenery of endless bamboo forests stretching across southern China. Standing in the middle of one, you're surrounded by thousands of smooth, perfectly straight trunks, reaching more than 100 feet into the sky. Sunlight barely filters through the thick leaves, casting a mystical green glow, and the only sounds are the soft whispers of wind and the gentle creaking of stalks brushing against each other. But bamboo's real superpower is its outrageous, almost indecent speed of growth. It's the rocket engine of the plant world. Some species, like the giant moso bamboo, can grow 3 feet in a single day. Imagine that. You could literally sit and watch it grow. In just a few months, a young shoot reaches full height. It's not a tree that takes decades. It's a giant grass ready for harvest in just 3 to 5 years. And here's the best part. When you cut one stalk, the root system stays alive and immediately sends up new shoots. This isn't deforestation. It's more like mowing a lawn, an endless, self-renewing resource. When harvest time comes, workers enter the forest. There are no roaring chainsaws or heavy machines tearing up the ground. Most of the bamboo is cut by hand, using simple saws or machetes. With a dry crack, the stalk falls to the ground. The branches and leaves are trimmed off, and the smooth, hollow green stems, called culms, are tied into bundles and carried out of the forest. This is the raw material, the uncut gem that's headed to the factory to be transformed into 1,000 different things. Bamboo is a true superhero in the fight against climate change. It absorbs carbon dioxide 35% more efficiently than most trees and produces 35% more oxygen. These 16 million acres of bamboo in China are giant green lungs working to clean the atmosphere. It doesn't need pesticides or fertilizers, making it one of the cleanest crops to grow. And unlike cotton, one of the thirstiest plants in agriculture, bamboo thrives on rainwater alone. Let's look at two of the most fascinating transformations. First, how do you turn a round, hollow stalk into a hard, flat floorboard, tougher than oak? The bamboo trunks are first cut into sections and fed into a machine that splits them into long, narrow strips, like a giant apple slicer. These strips still have a curved shape and outer skin. So they go through another machine that shaves off the outside and inside, turning them into perfectly rectangular slats. Next comes a spa treatment. The slats are boiled in hot water or steamed. Not for cleanliness, but to remove all the sugars and starches that bugs and mold love to feed on. After that, the sugar-free slats are placed in a drying kiln, where they're slowly and carefully dried to a precise moisture level. Now we have thousands of perfectly dry, sturdy slats. Time to put them together. The slats are coated with glue and stacked into a mold, where a massive hydraulic press comes down. With a force of thousands of pounds per square inch and high heat, it compresses the slats into a solid, monolithic block. From this block, manufacturers cut floorboards, countertops, plywood, and even structural beams. The second transformation is even more astonishing. How to turn this tree-like grass into soft, silky fabric for a shirt or bed sheets. This is industrial alchemy. The bamboo culms are first chipped into small flakes. Then, the flakes are soaked in a chemical solution, usually caustic soda, that breaks down the cellulose, the plant's rigid framework. After several hours of cooking, the hard chips become a soft, thick mass that looks like paper pulp. This pulp is washed, bleached, and pressed to squeeze out excess moisture. What's left is a sticky, dense gel. This gel is then forced through microscopic holes in a metal plate called a spinneret, like a giant molecular meat grinder. On the other side emerge ultra-fine, continuous threads. These threads drop into a bath of another chemical, usually sulfuric acid, which instantly solidifies them. Now we have silky, shiny fiber, bamboo viscose. It's washed, dried, and spun into yarn, which is then woven into incredibly soft, breathable, and hypoallergenic fabric. Now let's peek into the world of small eco-heroes, the birth of a bamboo toothbrush. It all starts with harvesting mature 4-year-old moso bamboo. The trunks are cut, then sawed into long, even sections. These sections are split into thin slats. Next, the slats are run through a special milling machine. Imagine a high-precision pencil sharpener. It shaves the slat into a perfectly smooth, rounded stick, the future handle. This process is incredibly fast, with thousands of handles flying out every hour. Then comes heat treatment. They're baked to make them more water resistant and to give them a beautiful caramel tone. Next step, the haircut. A machine drills dozens of tiny holes into each handle with surgical precision. Then comes the most fascinating part, bristle implantation. A machine, similar to a high-speed sewing machine, grabs a bunch of nylon or biodegradable bristles, folds it in half, and punches it into each hole using a tiny metal staple like an anchor. This happens dozens of times in seconds. The final touch, trimming. All the bristles pass through a trimmer to make them perfectly even or shaped. And that's it. Simple, brilliant, and much kinder to our planet. But these are just 3 examples. This green dragon has 1,000 faces. Young bamboo shoots are a delicacy in Asian cuisine. It's used to make billions of chopsticks, cutting boards, dishes. It's burned to create activated charcoal for filters. It becomes paper, blinds, furniture, even computer mouse shells. In construction across Asia, it's still used as incredibly strong, yet lightweight scaffolding for skyscrapers. And this entire ecosystem, from the farmer cutting stalks to high-tech fabric factories, creates a $27 billion economic phenomenon. But what does that mean? That's more than the GDP of some small countries, like Iceland or Jamaica, and the number keeps growing. Just 10 years ago, the industry was half the size. Projections suggest that by the end of this decade, the global bamboo market could exceed $100 billion, and China plans to stay its dominant player. This isn't just about a few big factories. It's an ecosystem that supports over 35 million people, from rural farmers to designers in Shanghai. It's a story of how nature's wisdom, multiplied by human ingenuity, can turn ordinary grass into an infinite resource that dresses us, feeds us, and builds our world. Every year, new icebreakers are launched around the world, giants capable of cutting through ice several meters thick. These are ships whose mass can exceed 20,000 tons, more than the weight of an entire stadium filled with people. But how is this steel beast born from 1,000 metal blocks? What does the moment look like when a multi-story crane, with millimeter precision, installs a piece of the hull weighing hundreds of tons? And what happens when the ship's bow first cuts into an ice field, and the hull shudders from an impact similar to an earthquake? In this video, you will learn what is not shown to the public, from digital ghosts in design bureaus to the moment of truth when an icebreaker meets its first ice. Watch until the end, because a secret that few know awaits you. It all begins not with the roar of hammers, but with the silence of a design bureau. Before a single piece of metal is cut, thousands of engineers spend years at computers. They create a detailed 3-dimensional model of the future vessel. This is a digital twin, where every screw, every weld seam, every meter of pipe is calculated. Using powerful computers, they simulate the most extreme situations. How the hull will interact with ice of different thicknesses. How the ship will behave in a hurricane. How it will withstand a collision with a multi-ton hummock. These are virtual crash tests, where the cost of an error is only processor time, not human lives. Only when every aspect of this digital ghost is perfected are the drawings sent to the workshop. Icebreakers are not built whole, like a model ship in a bottle. They are assembled from giant blocks, like a colossal Lego set. In huge workshops, the size of several football fields, the cutting of steel begins. For icebreakers, special low-temperature, high-strength alloys are used. Ordinary steel in the Arctic cold becomes brittle as glass and can crack from a strong impact. But this one retains its ductility and strength even at a temperature of -60 degrees Fahrenheit. The sheets of this steel can be incredibly thick. If a regular ship has a hull thickness of less than an inch, then an icebreaker in the so-called ice belt the area that contacts the ice, can have a thickness of 2 inches or more. This is thicker than a bank vault door. Plasma cutters, controlled by a computer, with a hiss and showers of sparks, cut thousands of parts of the future hull from these sheets. Then these parts are welded into sections, and the sections into huge multi-story blocks. Each such block is already a finished part of the ship, for example, a piece of the engine room, or several cabins, already with part of the pipes and fasteners. Every weld seam here is a matter of life and death, so it is checked with X-rays and ultrasound to ensure the absence of the slightest defects. A symbolic moment arrives, the laying of the keel. On a huge construction site called a slipway or a dry dock, the first central block is installed. This is the spine of the future giant, and to this spine, like ribs to a spine, other blocks begin to be attached. Giant gantry cranes, looming over the entire dock, come into play. With incredible precision, they lift these multi-ton pieces, weighing hundreds of tons each, carry them through the air, and with millimeter precision, set them in place. Welders, resembling astronauts in their protective suits, connect these blocks into a single, monolithic hull. Gradually, day by day, a giant steel beast grows from these separate pieces, and its shape is its main weapon. The bow of an icebreaker is not sharp, like a regular ship's. It has a special, spoon-like shape. It doesn't cut the ice. It crawls onto it, and then, under the action of the colossal weight of the entire vessel, and this can be from 15 to 20,000 tons, it simply breaks the ice, like a person stepping on thin ice on a puddle. Its bottom is rounded, without a protruding keel, so that after breaking the ice, it can easily push the fragments aside and not get stuck. While the hull is growing, the heart is installed inside, the power plant. An icebreaker needs not so much speed as colossal, unstoppable power and torque. Therefore, most modern icebreakers are diesel-electric. Imagine that a whole power station is inside it. Several giant diesel engines, each the size of a bus, turn generators, producing megawatts of electricity. This energy is then supplied to huge electric motors, located in the aft part of the vessel, which directly turn the propellers. This scheme allows for maximum power on the propellers instantly and very precise regulation. The total power of the power plant can reach 50,000 horsepower, enough to power a small city. The propellers of an icebreaker are also a work of art. They are made of super strong stainless steel, have a huge diameter, and thick blades like the wings of an airplane, capable of withstanding impacts from ice flows weighing tons. When the hull is assembled and the main equipment is installed, the moment of birth arrives, the launch. If the ship was built in a dry dock, the dock is simply slowly filled with water, and the giant ship smoothly floats off its supports. If it was built on an inclined slipway, it is much more dramatic. The supports are cut, and the multi-thousand-ton machine, gaining speed, slides into the water with a creak and a roar, raising a huge wave. And so, this giant for the first time sways on the waves. But it is still far from ready. It is just an empty steel box with engines. It is towed to a fitting-out quay, and here the most complex part begins, the outfitting. Hundreds of miles of electrical cables, thousands of meters of pipes for water, fuel, sewage, ventilation are laid throughout the ship, forming its circulatory and nervous systems. Living modules, wardrooms, a galley, a medical unit are installed. Navigational equipment is mounted on the captain's bridge. Radars, sonars, satellite systems. Powerful deck cranes, scientific equipment, a helicopter pad are installed. The entire ship is covered with a thick layer of thermal insulation. And then the time for the final exam comes. The icebreaker goes out into the open sea, away from the shore. On board, Not only the crew, but a whole army of engineers, representatives of the shipyard, classification societies, and the customer. Each of them with their own notebook and a list of hundreds of items that need to be checked. It all starts with the basics. Full ahead. The command sounds from the bridge. The engine room comes to life, the diesel generators go to full power, and the giant propellers begin to accelerate the multi-thousand-ton machine. Engineers with sensors check everything: hull vibration, engine temperature, pressure in the fuel systems. The vessel accelerates to its maximum speed on clear water, which is usually not very impressive, about 17 knots. Then the command, "Stop engine." And everyone watches how many miles this giant will need to come to a complete stop. This is called the inertial coasting. Next, maneuverability. Hard to port. And the rudder is turned to the maximum angle. Everyone watches how large the turning circle will be. That is, how wide a circle the icebreaker will describe at a full turn. They test reverse, reaction speed to commands, the work of the autopilot. Every system, from the large engines to the small pump in the toilet, is turned on and off, checked under maximum load. They even conduct a so-called blackout test. They deliberately turn off the main power to check how quickly the emergency diesel generators will start and restore the operation of vital systems. Only when every item on the long list is checked off. But all this was just a warm-up. The real exam is ahead. Winter comes, and our icebreaker, fueled to the brim, heads north, towards its true calling. The first encounter with the ice. This is the moment of truth. The captain directs the vessel straight into an ice field. From the bridge, you can see the horizon turning into an endless white desert. First comes young, thin ice. The icebreaker passes through it like a knife through butter, with a light rustle and crackle. But then the ice gets thicker. And so, the vessel at full speed crashes into real, multi-year ice several feet thick. A deafening blow sounds, shaking the entire hull. This is not like a collision. It's like the sound of an earthquake. The whole ship vibrates, dishes in the cupboards rattle. The specially designed bow crawls onto the ice, and under the weight of thousands of tons of steel, it breaks with a loud crack, spreading giant cracks. The fragments, the size of cars, scrape against the sides with a grinding sound. And so, meter by meter, the icebreaker makes its way. Special sensors, installed throughout the hull, record the pressure that the ice exerts on the hull and transmit the data to the engineers. They check whether the real loads correspond to those calculated in the computer models. It returns to port for final adjustments. Imagine thousands of glass threads, thin as a hair, combined into a single river, are transformed into a material that is already challenging steel. This isn't science fiction, but modern production of fiberglass rebar. Every year, the world spends billions fighting rust, repairing bridges and parking garages destroyed by corrosion. But there is a solution, a composite that is twice as strong as steel, 4 times lighter, and doesn't even know what rust is. The market for this material is growing by 12% annually, and today you will see how a building material of the future is born from hundreds of bobbins and a barrel of resin. It all begins at one end of a huge workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall, several yards high, hundreds, and sometimes thousands, of huge bobbins are installed in neat rows. On each of them is wound the thinnest glass thread, or roving. This isn't the glass that windows are made of. This is a special fiberglass, which is produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. They will be our skeleton, our internal army, which will give the rod its insane strength. From each of these hundreds of bobbins stretches its own separate thread, and they all gather into one thick, fluffy bundle. It's like thousands of streams merging into one large river. This dry white bundle is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Each of the thousands of threads must be tensioned with the same force. If one thread sags and another is over-tensioned, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment baptism in resin. The dry glass bundle is slowly immersed in a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin our meat that will grow on the glass skeleton. This is a complex chemical cocktail. The base is usually polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will start a chemical reaction and force the liquid to turn into a solid plastic. Also, various additives can be added here. Pigments to give color, ultraviolet inhibitors so that the rebar is not afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to soak every, even the tiniest fiber. The bundle must be completely submerged in this resin so that not a single dry spot remains. The soaked, heavy from sticky resin bundle comes out of the bath and heads to the point of its birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round, polished hole, the diameter of which exactly corresponds to the diameter of the future rod. The die is heated to a certain temperature. When the wet bundle is drawn into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass together, forming a perfectly round rod. Third, the heat from the die starts the initial stage of the chemical reaction of hardening, or polymerization. The resin begins to turn from a liquid into a gel. At the exit of the die, we already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special bundle of the same fiberglass is wound onto it. A thin, resin-soaked thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled on the sticky surface, which sticks firmly to the resin. Now our rebar has not only strength, but also teeth with which it will hold onto concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel, or polymerization furnace. This is a long chamber that can stretch for tens of feet, inside which a high temperature is maintained, usually 400 Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively connect with each other, forming a strong, rigid, three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material, which firmly binds millions of glass fibers into a single monolith. It's like baking a pie. While the rod slowly moves through this hot tunnel, it acquires its final, stone-like hardness. But what pulls it through this whole long path, from the bobbins to the furnace? At the end of the line stands a special pulling device, which gave the whole process its name. Usually, these are two caterpillar mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads and at a constant, precisely calibrated speed, pull it towards themselves. It is they who create the force that pulls the fiberglass through the resin bath, through the forming die, and through the furnace. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor appears an endless, perfectly even, hard and hot fiberglass rod. The final chord is cutting. Across the line is an automatic saw. It synchronizes with the speed of the rod's movement. At the right moment, makes a quick forward movement, and with a sharp whiz, cuts off a piece of standard length from the endless ribbon, for example, 20 or 40 feet. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And so, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and furnaces, have turned into a light but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungles. The fiberglass rebar market is not yet a giant like the steel market, but it is the coolest and most daring newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are simply insane. It is expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now about the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sounds boring? Now imagine it in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it is limited by weight. Or, for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can calmly carry whole coils or bundles of fiberglass rods, whereas a crane is needed to move steel. This is a colossal saving on logistics and labor. Second is strength, and here fiberglass simply enters the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing an ordinary rope with a climbing rope. At a smaller thickness, it withstands much greater loads. But the main trump card, the real superpower of fiberglass, is its war with rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load, it's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. Rust increases in volume and literally tears the concrete from the inside. Annually, the United States spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years, and a structure with fiberglass rebar is calmly designed for more than 100 years.